Hello, welcome. This is Mr. Tompkins' class. We're going to talk about forces and the laws of motion. So this is going to be your force video, and then we will discuss this next class period. This is going to be chapter 4 in your book, section 1, and it's titled Changes in Motion. We've already discussed motion in both one-dimension and two-dimensional areas, and we haven't really talked about the causes of motion, and so that's what the point of this whole lesson is what causes motion. Your responsibilities and the things that I want to see turned in today or next class period are just basically going to be your notes, and so this is what I want you to watch out for and to write down. And the things that I want you to put is like define force, and tell me 3 things that you can do to your car to apply a force to it. Give 3 examples of force listed in this video, and then draw the free body diagram from this video. And that will serve as our sample problem for our activity that we're going to be doing on Wednesday. So let's talk about this idea of force. And we're not talking about the dark side of the force or anything like that. Instead, this is the physics force. And it's a dynamic influence is the way that we define it. Dynamic means that it can change, and it influences other objects, and it causes an acceleration, or a change in an object's velocity. Forces are vector, and their directions point in the direction of the accelerations they create. And its unit is a Newton, named after Sir Isaac Newton, which actually contributed a lot to motion and contributed 3 laws of forces or 3 laws of motion that we will be talking about in this chapter. 1 Newton is roughly about 1/4 of a pound. And so we'll use that conversion factors later on in the year whenever we start talking about power. But right now, 1 Newton, a Newton is the units for forces, and so on. Now, on your car, I want to talk about, well, what does forces do to your car? Or what can you do to your car to cause forces on your car? And so a force changes an object's velocity. And we know that velocity has both a magnitude and direction. So that means that even changing the object's direction of travel requires a force, such as steering. And so that we can use this definition to determine what you can do other than like kicking your car to cause a force to act on your car or to accelerate your car. And those are, well, obviously press the accelerator or the gas pedal. This causes an acceleration in the same direction as your velocity, and so it speeds you up. We've already talked about that. When your acceleration and your velocity both agree, your object will speed up, and so the accelerator causes your car to speed up. The brake. This causes an acceleration opposite the direction of your velocity. And so when you brake, you slow down. And then the third one, which is kind of not most people think about, is just turning the steering wheel. Now this changes the direction of the velocity, but it doesn't necessarily change the speed. I know that we often connect the two because we slow down to make turns, but often we slow down so that we're not taking a 30-mile-per-hour turn at 60 miles per hour, so we don't run off the edge. And there's another physical aspect behind that we can talk about later. But turning your steering wheel is another way of applying a force to your car, because you have to apply a force to get your car or any object to change its direction of motion. Types of forces. There are actually 2 types of forces that we're going to talk about. You have contact forces, which are your basic pushes, and your pulls. And those are between objects that are actually touching each other. And then you had field forces, and these are more like the Star Wars movies in the fact that we can directly influence objects through a distance. So using field forces, we can manipulate objects at a distance. And we have gravity, electric field forces, and then magnetic. Let's talk about the field forces first. Gravity. Gravity is the one that we probably know the most about, or that we observe the most. And it's given a unit or a variable of capital F for force and then sub g, F sub g. Now, I've seen a lot of misconceptions where we start calling this force of gravity negative 9.81 meters per second squared. In fact, that's not true. Negative 9.81 meters per second squared is actually the acceleration of gravity. The force of gravity is the object's weight. And there's an equation that goes with that and calculations that we can do to figure out this force of gravity using the acceleration of gravity. Now, the force of gravity always acts on an object. There's no place that you can get away from the force of gravity, even in outer space. It's a common misconception that outer space, there is no gravity. But in fact, there is always gravity, and it always affects an object. And gravity always points straight down. So this will be the easiest one to pick out the direction of the force because it's always straight down or towards the center of the earth. And so if I look at these two scenarios here, I have a block on a table, and then I have the same block on an inclined plane. And if I were to draw my force vector on this block, it would look something like this. It would point straight down, and it would be in the magnitude of the weight of the block. And then if I move that block onto an inclined plane, once again, it'll point straight down, and the magnitude stays the same because the object, as long as it stays on the surface of the earth, will have the same weight. So the magnitudes are the same. The next one is the electric force. This is the force between two charged particles and if they're different charges, such as this one is positive and this one is negative, they're attractive forces, and so they pull towards each other. And if they're like charges, like this is positive and that one's positive, well, then they're repulsion forces, and they actually push away from each other. When we use the Van de Graaff generator, which I have a couple in class, or you've seen it done where you touch this metal sphere and then your hair stands up, that's what it's doing, is it's giving you these like charges on the ends of your hairs, and then they push apart. And then the third field force is the magnetic force. This is what's used to keep that A+ physics test that you just took on the refrigerator door. It's caused by these moving charges up here. So when these charges move, they create this magnetic field. And it also has opposites and similar, but we call those poles, and they have North Pole and South Pole. And it follows the same rules. Opposite poles attract, and like poles repel each other. Now let's talk about contact forces. The first one we're going to talk about is called the normal force, which is a capital F and a little n for normal force. And before I discuss this, I want to talk about, well, if forces cause an acceleration, why whenever an object sits on a table doesn't it accelerate through the table? Or why doesn't it fall through the table? Well, gravity there's always that force of gravity pointing down, so shouldn't that accelerate the object down? In fact, that's where this normal force comes in. It's what prevents the objects from falling or pushing through other objects. And they are always perpendicular to the two surfaces in contact. So whenever we go to determine the direction of these forces, we have to look at the two surfaces that are in contact. And so if I look at this first one with the block sitting on the table, the surface in contact is right here. This is where they connect to each other. And if I were to draw a force on the block by the table, perpendicular to that, well, it would shoot straight up. Just like that. And so it goes straight up. And notice it is at a 90-degree angle to the surfaces in contact. Now if I look at this block once again on the inclined plane, well, now the surfaces in contact are at this angle right here. They don't go, it's not flat, it's not horizontal, it has some vertical and some horizontal component to it. And so its normal force actually will skew up to the left a little bit. Now notice also that the magnitude of this normal force is changed. Same block, same weight, but the normal force can change depending on the angle of my ramp or my incline. And it always points perpendicular 90 degrees to the surface right here. Now if I look at this last scenario where I've taken this extreme angle right here and I flipped it all the way over, and so now the block is being pushed up against the ceiling, well, here's the surface in contact, and the normal force is going to point straight down. So it points straight down. And once again, it's 90-degree angle to the surface it's in contact. The next one is a frictional force, or capital F sub F, so F sub F. And there's actually two types of friction forces, and we'll talk a little bit more about those later in this chapter. But right now, we could just call it a friction force for the activity that we're going to be doing. Now, this is the force caused by objects sliding or wanting to slide across each other. So if they have this tendency to want to move, there will be some friction involved. And then the direction of these are always parallel to the surface of of the connection. So right here, like on this block, the surface is here. It's always parallel to the surface in contact, and it's always opposite the direction of movement or the tendency to move. So if I have this block and I want to push it to the left, so I'm pushing it to the left, well, the frictional force will be to the right. And then likewise, if I want to push this block to the right, its frictional force would be to the left then. If I look at this instance where I'm on an inclined plane, think of this as a toddler on a slide. Now a toddler, whenever you put it on a slide, put them on a slide, actually slides down the slide, and so the tendency for the toddler to move is going to be down the hill or down the slide. And so that means that opposite the motion is going to be the friction, which points up the slide. Now another force that we're going to talk about is the tension force, or capital F sub T, and this is any force that's being applied to an object by a string, and it's always along the direction of the string. Now this is not really something that's too important at this juncture, but we will be using it in the activity, so we just need to know that it's force of tension, and it goes along the direction of the string. And then for all other forces that we encounter that we haven't discussed so far, we're just going to call those applied forces, or capital F sub ap. So the applied force. And this is going to be any push or pull that is foreign and not covered in what we have done, what we've talked about so far. We'll just call that force applied. Not the force that we were talking about, just in case you got confused. So let's move on. Now let's talk about this idea of net forces. In order to understand net forces, we have to look at addition of forces, or vector addition. And because forces are vectors, they add just like vectors. For now, it's sufficient to look at the head-to-tail method of adding vectors. And so I'm going to review that with you real quick, where I have this black vector pointed at that direction, and adding to this red vector, which is pointed down in that direction. And to use the head-to-tail method, I'm actually going to take the tail of the red vector, and I'm going to place it on the head of the black vector. And it's going to look like this, just like that. So it moves over, and it goes head to tail. And then my answer, or what I call the resultant, is a line or an arrow that's drawn from the free tail to the free head. And so it's going to be a line that's drawn from here to there, and it's going to point in that direction. And so if I look at this, you'll see that my yellow vector actually completes the triangle, and that is my resultant or my answer. And we're going to use that in this activity to come up with net forces. Now these net forces lead themselves to balanced and unbalanced forces. When you add all the vectors, you get what's called the net force that acts on the object. If there is an unbalanced net force, or there is a net force, then the object will accelerate in the direction of the net force. So that means it'll start moving, or it'll slow down or speed up, depending on what its velocity is, in that direction of the net force. And then likewise, I can flip that and say, well, if the object is accelerating, or the object is speeding up or slowing down, then I know there has to be a net force. If there is zero net force, so I add up all the vectors and they all cancel out, then its velocity doesn't change. So either it's at rest or it's moving at a constant speed. Likewise, if it's moving at a constant speed or it's at rest, we know that all the forces have to cancel out. And so this will lead us to coming up with relative magnitudes of forces later on in this activity. Now this is the activity we're going to be doing, and this is the free body diagrams. Basically, we're going to use free body diagrams as a tool to analyze all the forces that act on an object. We use it to determine which direction and how much net force is on that object, as well as determining what objects are applying forces to that object. So we look at this by three major steps. First one is we want to represent our object as a single point. Now we call this single point the center of mass. So if we could sum up all the mass of that object into one point, where would it be at? And we usually use where it balances at, because that would be the center of its balance, center of mass, center of balance, roughly the same thing. So we're going to represent all the object as a single point. And it's real simple. All you have to do is put a dot, and I'll show you. The step two is we're going to determine all the forces that are acting on our object. their directions and their relative magnitudes. And we're going to use this, the idea that if the object is accelerating, well then one force has to be longer than the other one. And if the object is not accelerating, it has a constant velocity or remains at rest, then we know that all the magnitudes have to somewhat cancel out. And then step 3 is we're going to draw our force vectors on our object. So if I look at this, here is the example problem, so make sure you write this down because this is what I want to see. And we're actually going to see this again on Wednesday, or in the next class period. The object is pushed to the right. So this is what it's telling me. It's telling me that somebody is pushing the object to the right. And this is my object right here. One of the things I want to note is that if you look, these lines are, let's say that these lines are taken at 1 second intervals. So it covered that distance in 1 second, and then it covered that distance at 1 second, and then it covered twice the distance in 1 second, and then 3 times the distance in 1 second. So we can look at this, so we know that the object is going to be speeding up to the right. And then that's going to have a profound impact on how we draw our free body diagram. So there we go. I just moved the picture down here, and we're going to work through the steps. Step 1, represent our object as a single point, which I did. It's right there, that little black dot. That is our object. Step 2s and 3s, determine what forces are acting on our object. Well, the first force that acts on our object, well, it's the easiest one to always do, and you always put it on there. It's the force of gravity, and it always points down, pointing down. And I labeled it F sub g. Now, the object is not falling through the table. If it was falling through the table, well then there would be some serious issues with this table right here and not really being a table. So instead, there has to be something that is canceling out this force of gravity, pushing back up on the block, and that is going to be our normal force. And it's this red vector right here. And because the block doesn't fall through the table or lift up into the sky, we know that the normal force has to equal the force of gravity. And they have to cancel out. So if I were to add these two up using the head-to-tail method, they would cancel each other out. And the normal force is labeled F sub n. After this, I know that because the object is moving, there has to be some frictional force. There's a movement along a surface here. And so here's my surface. Parallel to the surface is going to be this way. And because the object is moving to the right, I know that the frictional force has to be to the left. All right. Now, I drew a small arrow here because I know that the object is speeding up to the right. So that means that the force to the right has to be greater than the force of friction. So I just chose a smaller arrow for the force of friction. And then the last one is going to be my push, or the force applied, the force that I'm applying to it. And this is because it tells me to, or it says that I'm doing it, or it's being pushed to the right in my problems. So because it says so. And it has to be larger than my friction because the block is speeding up, or it's accelerating to the right. So if I look at here, once again, these lines, they're getting farther apart, and so the block is speeding up to the right. And so that is how I do this free body diagram. I start with gravity. I counteract gravity with my normal force if I have it. I look to see if the object is moving. If it's moving, then it has a force of friction. Or if it's wanting to move, then it also has a force of friction. And then if another object is pushing on it, then it has an applied force. So I look at for all of these vectors. Now if I were to do the head-to-tail method and move this green vector up here, it would cancel out. And then if I move my blue friction vector over, it would cancel out a little bit of this force applied. But it leaves me still a net force in the direction of the applied force, which causes the block to speed up. Okay? Make sure you get this all put in your notes. If you don't have it, make sure you rewind and rewatch. This is roughly around 19 minutes, so it's not too long of your time. I do encourage you to go back if you don't understand and see if I answer your questions and you just missed it. Or if you have any questions, write them down and ask them in class, next class.